derivatives to show you today, and I have 4.4 day 1 notes pulled up. We're going to do derivative of exponential functions. These are exponential functions, and logarithmic functions. These are logarithmic functions. You have derivatives for each one to memorize, and I'm gonna show you your favorite one yet. And keep in mind, I'm going to show you the simple derivative where it's just an x that's in our function, and then what if it's not just an x and it gets messy? And then I think you can figure it out, but I'll go ahead and show you what to do if it's not just an x but it's messy. So, for your simple derivatives, this is going to be your favorite one. The derivative of y equals e to the x, y prime equals e to the x. Oh my goodness. How is that even possible? Well, I'll show you in a minute. Now that's if your base is e. Now remember, e is a constant, 2.71 something, and x is in your variable. So don't be crazy and try to power rule this. Don't be crazy and try to bring your x down in front and call it e to the x minus 1. No. That's for a polynomial. That's when your base has the x in it and your exponent has your constant. This is different. This is our constant in our base. Our variable is now in our exponent. The function a to the x. A could be any constant. This could be 2 to the x, 10 to the x, 11 to the x, whatever. Okay? The derivative, when you have a constant to the x power, it's going to be really similar to e. So it's going to start out the same. But then it goes times the natural log of a. For example, if this were 2 to the x power, my derivative would be 2 to the x times natural log of 2. What's natural log of 2? I don't know. It's some constant. If this were 7 to the x, its derivative would be 7 to the x times natural log of 7. What is natural log of 7? I don't know. I would need a calculator to find out, but it's a constant. Okay? So, in fact, if it's a constant, some of you would prefer putting this out in the front. But then I would hate for you to touch, I don't know, just leave it like that. All right, natural log of x, you're going to like this one too. The derivative of natural log of x is y prime equals 1 over x. And that's if your base is e. That's if the base of your logarithm is e. What if your base of your logarithm is something besides e? Then your derivative is going to be 1 over x, and still in the denominator, times natural log of a, whatever that base was. Those are going to have to be memorized. And now, I think you can figure this out on your own, but I'll go ahead and go through them with you. What if it's messy? Well, your derivative, y prime, is going to be e to the messy, right? We don't touch the messy. The first, when we're doing the derivative of the outer, when we're looking at big picture, do the derivative, recognizing it is messy, we don't touch the messy. So we got e to the messy times the derivative of the messy. What if it's some other constant to the messy power? Its derivative is going to be a to the messy. Remember, don't touch the messy. finish out your derivative, times natural log of a, and then chain rule it. Derivative, messy. I mean, since it's all multiplication, you could have done a to the messy. You could have gone ahead and done your chain rule and then done your natural log of a. It doesn't matter. What if what you're taking the natural log of is messy? Well, then your derivative is, instead of 1 over x, now it's 1 over messy times the derivative of the messy That's if your base is e. If your base is anything besides e, log base 10, log base 2, whatever. Hang on. Sorry, didn't label that one appropriately. Next one, your derivative is 1 over the messy times the natural log of a. Remember, a is your base. And then chain rule it. Times the derivative of the messy. Now, just a little bit. I'm going to go back to the simple derivatives and just kind of talk to you about them for a little bit. I wonder why, if this is a constant and this is a constant, why are these two derivatives different from each other? I mean, it's the same concept, right? Y equals a constant to the x. Y equals a constant to the x. What's so special about e? Do the derivative on this the same way you would do the derivative on this. Ready? So what if this is an e? Here I go. Y prime equals e to the x times natural log of e. It's just one. We are doing them the same way. You're just not going to want to write times natural log of e every single time you do that derivative. Why don't we do this derivative the same way we do this derivative? If here the base is just a constant and here the base is just a constant, why don't we do them the same? Why don't we take this one times natural log of, oh wait, we do. It's really 1 over x times natural log of e. But you don't have to write that because natural log of e is just 1. Cool? Memorize them. Now, before going on to the examples, I know you just want to get started, like show me how to do it. I want to show you something. I want to show you something that's kind of cool. I have 4 things on the board, and I need to, let's see if I can keep that. I need to scoot. I need to turn the projector off. Scoot you over a little bit. There we go. And I'll turn a few more lights on. All right. Let me show you something cool. Ready? You all are supposed to know what the graph of y equals e to the x looks like. Think about that for just a minute. 9 minutes. Y equals e to the x. You should know what that looks like. That's what it looks like. Y equals e to the x. Think about some points it passes through. That one you're supposed to know, just like automatically. You were automatically supposed to know that any exponential equation, with any base passes through the point 0, 1. So you all know that when x is 0, y is 1. Let's look at some other points on here. What about when x is 1? I have the point 1 comma e to the first. What about when x is 2? I have the point 2 comma e squared. Right? So this is like 1 comma 2.7-ish. This is like 2 comma no, 2.7-ish. This is like, I don't know, whatever e squared is. Okay? So you got x values and y values on this function. Now here's what's cool. Let's look at the derivative. The derivative is e to the x also. What does this represent? This represents the slope of the tangent line to this function. So if I were to look at some tangent lines, maybe I'll look at the tangent line that passes through the point 0, comma 1. Or maybe I'll look at the tangent line that passes through the point 2 comma e squared. You know what's cool about those tangent lines? The slope of the line that passes through the point 0, comma 1, the slope of the line, the slope of the tangent line is the exact same as the y value of the function. Whatever the y value of the function is at 0, that's the same as the slope of the tangent line. Whatever the y value is of the function at 1, that's the slope of the tangent line at 1. This is the only function that has that unique property, where its slopes of its tangent lines are the exact same value as the y value at that point. Isn't that kind of cool? Oh, you think that's kind of cool? Now, let me show you some derivatives. Now, I would, this is kind of funny. I would teach this section like I first started teaching calculus. I would teach this section, I'd be like, everybody's going to memorize the derivative of y equals e to the x. You already have. You've already memorized the derivative. Like, you haven't even practiced it yet, and you already know it. It's your favorite one. If you can memorize that one, you can come up with the other 3 if you know anything about exponential functions and logarithmic functions. So, I started showing this to people to be like, hey, you can, don't worry about memorizing them, you can come up with them. And then I realized everybody's like, no, Ms. Neal, we can't. Well, okay, so maybe you're not going to remember all this, but it might be cool just to watch. Maybe. I don't know. We'll see. Do you agree with me? Okay, this is going to take you really back to some semester 1 pre-cal days. Do you remember how if my function is a to the x, do you remember in pre-cal when you worked with logarithms? E to the natural log of something, you all were taught how to manipulate it. You were taught how to change it all around. Here's what your takeaway was. Here's what your takeaway was. Oh, these like cancel, don't they? Oh, they cancel and I'm just left with a to the x. Well, okay, yeah. That's why I knew that this and this are equivalent functions, okay? So I don't want to cancel it. I want to complicate it for just a minute. E to the ln a. I just want to take you back to pre-cal when I just want to show you how this function is equal to this function. Okay, so ready? Before I do this, one more property of exponents, logarithms. Remember how you can bring your exponent down to the front? Hopefully you remember that. Now, this is messy. This is a function, y equals e to the messy. And in the messy, keep in mind, I have x times natural log of a. What's a? A constant. What's natural log of a? A constant. Very good. Ready? Derivative y prime equals e to the messy times the derivative of the messy. How do you take the derivative of x times a constant? It's just a constant. I'm going to take that back the way I had it. Okay with me doing that? I put the x back up as an exponent. I took it down for a reason. I put it back up as an exponent. And now you're like, oh yeah, they cancel. Whatever. This is where that derivative comes from that you just wrote on your paper in your notes. Isn't that cool? I just kind of, instead of a constant to the x, I just kind of rewrote it as e to the ln, manipulated it a little bit, took the derivative using my e to the messy knowledge. That's the derivative. Okay, let me show you another one. Y equals natural log of x. I'm going to flip it around. You'll see y in a minute. Natural log of x equals y. And what I showed you to do in pre-cal is, don't know much about logarithms? That's okay. Change it to an exponent. Grab the base. Do that. So I get e to the y equals x. E to the y equals x. Whoa, hold on. Y is my function. Y is like a messy function. X is my variable. Keep that in mind. X is my variable. Y is a function. Let's do a derivative. You're like, but wait, the y is buried. Yes, it is. That's okay. We have implicit differentiation for that. Okay, so ready? I have e to the messy. What's the derivative of e to the messy? It's e to the messy times the derivative of the messy equals the derivative of this side is 1. Let's solve for y prime. Y prime is equal to 1 over, divide by this. Wait a minute. That's not the derivative I had you write down in your notes. No, but you know what e to the y is? Cute. Same premise. Log base a of x equals y. Pre-cal. I get a to the y equals x. This is messy. Do a derivative. A to the messy times natural log of a times the derivative of the messy, right? A to the messy, natural log of a times it equals the derivative of this side. Divide. Wait, what's a to the y? Cute. That's where those come from. I don't always prove the formulas that I'm showing you, but I figured these were kind of proofs that you can kind of follow. Some of you can like do them on your own. Like some of you, if you forgot something, you could totally do that. I think most of you are going to prefer to memorize them, but whatever, to each his own. Okay, sorry, took up a little bit of your time there. Let's go back to the notes. Scoot you back over here. Here we go. Messy. Let's do a derivative. The derivative of e to the messy is e to the messy times the derivative of the messy. So 1 plus 2x. And if you write it like this, you're wrong. This is a binomial. You need parentheses around that around that binomial. You can write it like this, or you can put the 1 plus 2x in the front. Probably looks a little better that way. Okay. Next one. Do the derivative. And when we do this, there's always somebody in the class who's like, oh, I know what to do, You've got to product rule it. Good one. You've got to use 1d2 plus 2d1. Good one. No, you don't. E squared is a constant. This is just a constant with x. So e squared is actually the coefficient of x. Tricky. Y prime equals. My derivative is going to be the constant minus the derivative of e to the x is e to the x. Woo-hoo. Moving on. Messy. The derivative of 3 to the messy is 3 to the messy times the derivative of the, nope, hold on. Sorry, didn't finish my derivative. Times natural log of 3, there we go, times the derivative of the messy. Can you remember what the derivative of cotangent is? Ooh, some of you can, some of you can't. Negative cosecant squared. There's a negative in my term. The constant in my term is ln3. Many people would prefer to see the constant and the negative out in front. So I could rewrite this as negative ln3 times, times 3 to the cotangent x times cosecant squared x. All right, next one up. Now you do have to do product rule. One d2 minus 2 d1 and minus the derivative of x is just 1. that's a 1 minus ln x minus 1d2 plus, my bad, 1d2 plus 2d1. Sorry, let me back up. 1 d2 plus 2 d1 derivative. There we go. So that times that is 1. I still have plus ln x. I still have the minus 1 from over there. And I've got y prime is simply equal to ln x and last one. This isn't just log x. This is messy. So here we go. Y prime equals 1 over the messy times the natural log of our base, so times the natural log of 5, times the derivative of the messy. So I'm going to power rule it. I'll get 1 half x to the negative 1 half. Okay, so let's see. That stays, that's the denominator. That's going to go in the denominator.